it's not my dog's time to eat yet, so I'm back here for the last video on this class. So now I want to discuss the out-of-sample and cross-validation, and what are the advantages and the disadvantages. And I wanted to show you that the techniques are not going to solve the identification problems. And remember, read, these are all optional videos. I think it's important to see them and do them once in your lifetime. Let's now concentrate on the out-of-sample and the cross-validation. And it's clear that there will be some limitations about these techniques, but there are some advantages. So let's think about it. What is the purpose of the out-of-sample testing or a cross-validation? And the idea is that I want to understand the stability of the model, truly. I want to estimate in one sample and determine if that estimation, that approximation that I have in one sample, somehow is useful in a different sample. So when you think about it, that is truly testing if the function that we have estimated in one data, the approximation in one data, it can be extrapolated or be used or in a different data set. Is the model stable in the two samples? And there are some cases where we will think that it makes sense to ask that question. There are other cases in which it makes no sense to ask that question. So estimating in a group of men and then pretending that we can use that to estimate for women, very unlikely that will be true. And if you estimate for low-income households and then pretend to use that for high-income household, we would say, well, that makes absolutely no sense. So the fact that the model is not stable, in this case, is explained by the fact that the two samples are different. So when we construct these testing and training data sets, it's important to understand what are their characteristics to be able to understand whether or not we can extrapolate the approximation in one data to the prediction on the other. The heuristic of almost all the out-of-sample and cross-validation is that we're going to split the data. Hopefully we split the data randomly, and the reason why we do that is to make sure that the two samples somehow are identical in every respect, except the fact that one belongs for the estimation part, the training, and the other one belongs to the testing part, the testing. So in time series, this is very complicated to do, because truly, if you randomly pick days of the year and you extract them, see, because the variables are serially correlated, having the data on Monday and Wednesday, that tells me a lot what is likely to be the data on Tuesday. And therefore, in time series, constructing random subsamples, random split is extremely, extremely hard. In fact, my advice always is just to pick a time t, and everything before is a training, everything after is a testing. That's kind of, you do it doing that. In the cross-section is also sometimes hard to do. You have to make sure that you do not select on geography or individual characteristics when you're doing this. So the cross-validation I absolutely love, in the sense that it gives a chance to every data point to belong to the testing part. Many times when you have a horrible outlier, if you include it in the regression, it's just going to be forgotten. We're not going to use it. And this is especially true depending on the way or the form that you estimate. In a decision tree, for example, these outliers are going to be completely disregarded. But you see, in some point, having the super strong outlier in the estimation does not affect the approximation that much. But if you put that same observation on the testing, you might reject the model. Let's assume that you divide the data in k different sets, and then you use every set as a testing. So you estimate using data D1 to DK minus 1, for example. All those data sets you use for the estimation and the approximation, and then you test on the DK, then you test on the DK minus 1, the D2, D1, etc. You test on all of that. And the idea is that you compute the errors in each of those. And therefore, when you're comparing different models, what you're doing is comparing the models on the errors of the data that was not included for the estimation. What means to reject? So the idea is we are going to estimate a function, and here I'm just doing this very general because, this is a linear model, will be just a function, but we're trying to estimate a function to minimize the errors or the distance between the data and our prediction of the data, and we use the trained data, and then we take that function and substitute it, and we're going to reject if the errors are just too big. Okay, so first very important question, which is important to me, is can the misspecification of a model cause a rejection? And the answer is, I love it, is it depends, okay? So it depends on many things. So the first one is, if the misspecification is the same in both samples, then the cross-validation will be passed, the out-of-sample will be passed, and you will estimate perfectly the wrong coefficient. So in other words, in the examples of the error chain variables that we have a beta that was 0.5, but our estimate B was 0.2. That was the bias downward. And in fact, if you create a new 1,000 points, the estimate will be 0.2. It doesn't matter what you do, you will get 0.2. And the reason is that the B hat that you are estimating is the true beta minus the beta sigma eta divided by sigma eta plus sigma epsilon, sigma z, all of those to the square. So in this model, the bias is constant. You are constructing the bias with the same sigma eta, same sigma z, and same beta. Now, if you have, for example, if the parameters change, if the beta change, then the cross-validation will detect it. So if the beta changes, then the bias will also change, and therefore you will be able to detect it with the cross-validation. In other words, if the beta is different in the two samples, you will see that, and then you will reject. It is also possible that the sigma eta or the sigma c are different in the two samples. So if the volatilities are changing, if the heterochalasticity is happening in the data, then the biases are going to be changing, and you will be able to reject. But you need that to happen to be able to reject in the cross-validation. Other than that, you will just pass the exam. There will be no rejection, okay? So the rejection only happens if the bias or the parameters are unstable in the sample.